All right. Well, happy Thursday. We're cruising. So Tuesday, again, sorry, I had the video here on recursion. We'll talk more about recursion today. And then our lab next Tuesday will be on recursion. Apparently Tuesdays are cursed, though. We had our lab the first Tuesday, and then I was ill, sick, unconscious from a bad medication mix the next Tuesday. Then we had a snow day this Tuesday, and next Tuesday I'm out of town. Very sorry. It should be the only time I'm traveling this semester. So I'll have another YouTube video for you, and I'll have a lab assignment you can start working on. If you got questions on it, let me know. We can always talk about it the week after or that Thursday as well. Let's some practice on recursion, because recursion will be the topic of the next project that we start next week, because we've got the project coming up. Let's see, that is our project 0 is due next Thursday. Yeah.
For like the Linux lab, are we gonna do something like in lecture, or like the description said to like wait until lecture or something?
Oh, so if you don't have the VPN on your computer, you can't do it unless you're on campus.
Okay.
So I assumed if you were at home for the snow day, like you can go install the VPN if you want. Go for it. There's a bunch of extra steps, and it's just an exercise in using Linux, so we can do it now that we're on campus.
Okay.
Yeah, it's just following the steps, playing with it. One of my students posted they got this really cool sticker pack of a bunch of like open source stickers, and one of them was Vim. I really want to get some Vim stickers and just hand them out to people after they pass this Unix lab. Be like, all right, now you can tell everyone you used Vim. But we'll see. I got to see if I can order them. And then quizzes. I'm supposed to have quizzes here. You get points for the quizzes. Apologies. I had to go export and import and forgot about them. So we've got a syllabus quiz, which is basically free points. One of the things you do is acknowledge the academic integrity policy, where if I have to fail people, I get to show the dean, look, they agreed to the policy, they understood what the policy was, and here's where they cheated. So that's the big reason for that. And then we've got quizzes as we go through the chapters. I'll turn these on as we get there. So the chapter 2 quiz is out there. If you don't make it by the 30th, it's not a big deal. But usually it'll be once a week. We'll have a quiz. So I know I just sprung these on you. So if you need more time, take more time on it. It's okay. Not a big deal there. All right, and then let me reorder that. There we go. Yeah, cool. So we'll talk about recursion. We'll spend some more time with that. And then next week, we'll have another recorded video. We'll have the lab on recursion. And then we should be in pretty good shape. That sound good? Okay, cool. Sorry, I got gum in my mouth. It's all squeaky right now. I'm getting low on coffee. All right, let me pull up PyCharm here and make sure I've got the repository. So did I add? I didn't add the recursion stuff. Give me a second. I gotta get that code here then. Oh goodness, I don't even have it here. Oh, this one. I can give you this code here real quick. So I'm just going to move this over into that other repository. Recursion, sweet. All right, cool. So now we got that code out on the GitHub repository for you. So this should have been the stuff that was in the video on recursion in doing the maze solving. Did we get that far? Does this ring any bells?
Well, I think it's sharing. Yeah.
Yeah. Thank you. You probably want to see my laptop. This whole time I've been talking. I just made a joke this morning about how I forgot that, and I have to look at the screen. And I forgot to look at the screen. Okay, it's all right. It's all right. We'll get there. Yeah, okay, sure. So we got stuff. Wow. All right, let me go open the recursion project here. GitHub. GitHub. Oh, not that one. That's right. Documents, then GitHub. Documents, GitHub. I got too many GitHub folders. This is my mistake. Here's recursion. Okay. So maze solving. This idea of building out a little maze for us to solve and then using recursion. So backtracking recursion is not a good technique for solving mazes, but it's a very easy way to understand this recursion process. That's why I really like it. So in the real world, we don't ever solve mazes like this because it's terrible performance-wise. But it's a nice little easy step for us to kind of think through how this works here. And we'll do another fun little exercise on a puzzle we can solve using recursion that works out pretty well. So the idea with the maze, let me make it a little bit bigger, is we're just going to try everything, every single possibility. We're going to try until we find a solution. And if it doesn't work, we just undo. So this idea of backtracking, the undo step is the backtracking. So when we go and solve the maze, you say, okay, let me go find where the maze starts. Find the start character, right? Because we've got a couple different characters we're using. So we've got a start, we've got an end, we've got a wall, we've got our breadcrumbs, we've got open. So just a couple, these are technically static, they're class level, they're not self attributes, right? So they're defined in the maze solver class. They live once here, so if I have 50 different maze solvers, I still will only have this loaded once in memory.
Is it like a brute force?
Yeah, this is the brute force solver, yep. So once we find the start character, we're going to solve it using our private recursive solve function. A lot of times, recursive functions need lots of attributes. We need lots of information as it recurses. I don't want someone to have to tell the maze solver to solve at a specific row and column. To make it easy for them to use, they just need to call solve. I'll go find the start row and column. So a lot of times we have the public function and then we have the private helper function. Right? That's usually the easier way to go about it here. And then we say, hey, if there's no best solution, it's unsolvable. If not, we can return that here's the solution, right? This best solution idea. So the private solve method here this is the recursive piece. So we're going to call this and call this and call this and call this and call this. So eventually, if the maze is too big, this will crash because you can only have so many levels deep of recursion before Python quits on you. It can get pretty big, but by the time it's that large, it's just too slow to solve anyway. So we're saying, okay, if we're not at the start, we've taken a step. This way we're counting how many steps it takes to solve the maze. So if we're not at the start, count the step. If we're at the end, we're done. Right? If we reach the ending character, we're done. Then we can say, hey, if there's a best solution, or if there's not a best solution in this case, set it to be the string version of myself. So we have a little string function here that we can override the string function from object, which gives us garbage, with something pretty. So in this case, it's this ugly string join nonsense here. So we're taking every row in the maze, turning it into a string, putting new lines between them. And then we add in another new line. We say solved in how many steps, the number of steps. So we know, okay, here's the solution at this many steps. Because the idea here is we're going to try and find every single possible solution to this maze. I want to know the shortest path here. That's the idea, is how do I find the shortest path? Okay, so we save the best solution if it's not there. Otherwise, if we do have a best solution, see, is my step count better? Right? The best solution step count, is that better than the number of current steps? If it is, great. Now, if the best solution step count is greater than the number of steps. So I've worded this a little bit, I probably would do it backwards if I did it again. So my current number of steps is less than the best number of steps. But my current best and my current solution. If the current solution is better than this one, right? If I have less steps, then it's the best solution. It feels weird that the arrow is the other direction here. That's all. And then set it again here. So if it's not, then I ignore it. I already have a better solution as my best solution. I'm just going to ignore it. If it's not the end, so this is if I found the end, just track that I reached the end, see what happens. If it's not the end, now we're going to start doing some things. So if it's not the start, put a breadcrumb down. The idea with these breadcrumbs are to make sure I don't go up, down, up, down, up, down, up, down, up, down, up, down in an infinite loop. Right? You don't want to step on a breadcrumb as you're solving the maze. Right? So if you find a breadcrumb, we're not going to go there. So I put the breadcrumbs down to mark that, hey, I've gone on this path. Right? After I've done the breadcrumb, and I just don't want to overwrite the start character, because otherwise the solution looks funny when you print it. Then we're going to just try going up. So from every location we try, the very first thing we do is we're going to try, can I go up? If I can go up, then I'm going to recurse at that location. So I'm going to call the solve function again with row -1 to go up a row. Remember 0, 0 is the top left, because Python land is not math land. There's no origin, right? So this is row 0, column 0. This is row 1, column 0, row 2, right? So rows go up as we decrease to 0 as we go, right? And then whenever this is done, we come back and then we say, okay, can I go down? So because it's trying every single possibility, we tried going up. I may or may not have solved the maze. Great. Now I'm going to try going down. See, can I solve the maze from here? So as I go at this location, I'm going to try up. I can't go up. I'm going to try down. I go down. Okay, so from here, I'm going to say, can I go up? No, I can't go up because there's a start character there. Can I go down? Yeah, I can go down. Right? Let's try going up. I can't go up. There's a breadcrumb. Can I go down? Sure, I'll go down. Yeah, can I go up? No, I can't go up. Can I go down? Sure, I'll go down. So we're going to put ourselves into this position here of adding all these breadcrumbs here in the maze. Eventually, we're going to get to here. So we've gone down to here, and our maze solver says, okay, can I go up? No. Can I go down? No. Can I go right? No, there's a wall there. Can I go left? No, it's out of bounds. Right? If it's not the start, undo. Put the breadcrumb, take the breadcrumb away. Because it's not my current path anymore. I'm no longer on this path. So it replaces it back with the open. Yeah.
How does it change from one list to the other?
It's always using the same list. So self.maze, when you create a maze solver, is the maze that you give it. So when I give it this maze, when I call maze solver, I hand it this. It has that as that class level attribute. So it's always operating on the same two-dimensional list.
Well, like it's a list inside of their list, right?
Yeah, a list of lists. So a two-dimensional list. So I've got rows and columns essentially.
Like how does it go from one row to the other?
So like maze at the row index is the row. That value is another list which has an index that I'm going to call the column here. So I use both the row and the column indexes when I access the two-dimensional list. Because really the first one is a list of lists. So I get the list, which is I'm considering the row, and then that is a list of what I'm calling the columns. It has its own set of indexes. So, and doing it this way is nice because I could have like weirdly shaped mazes. I could have rectangles. I could have ones that are longer than others. Like, they don't all have to be squares. A square is easy right now. Yep. So, yeah.
So now you're explaining that's fine, but later on, will you just debug and show us like one step at a time so that?
Yeah. So I'll show you. We can make it print one step at a time. Yeah. So if we have gone all the possibilities, we're going to mark it as open. So we're taking that step away. So I get back to here, and I'm done. So where it goes back to, remember we keep the list of calls to functions. Python keeps that on the stack. There's that call stack. It says, hey, I was here at this line number, and I jumped to this function here at this line number. Well, recursive calls just keep adding to that stack. When this function is done, and you can't do anything else here, the else is done, right? We go to take away a step. Because I've undone that breadcrumb, I'm going to take away that step, and then this function is done, it can go back. So as we watch it go, let me put a breakpoint in here. Let me take out these breadcrumbs, sorry. Let me do breakpoint here. Let me run this one in debug mode. Oh, it needs a Python interpreter, come on. I don't think it matters, right? I'll just run it. Oh, come on. Sure, use that one. Really? 312. All right, I messed it up. Hang on, let me go to my settings. I probably should have looked at what I was picking there. Bless you.
Thank you.
Python interpreter, show all. Sure, Python 312. I said not that one. All right, hang on, edit configuration. Yes, okay, so I don't want that one. I want 312, sure. Doesn't really matter. Okay, so we're about to call solve. So here's the maze. Right, I've created the maze solver. We've called the init here. So I'm going to step into, because I want to see what happens here. So right now, this is the call stack. I was at line 21 of my main script. Now I'm at maze solver line 64. This is the public solve function here. So this is going to go through and find the first start character. I stepped over, didn't I? I did a bad thing. Hang on, sorry. Let me, I want the debug breakpoint here. There we go. There. So I'm going to step into solve, and step, step, step. Now we're ready to solve at row index 0, column index 0. So I'm going to step into this one. Here we go. So now we have the maze, right, at this list, right? It's a little small here. Sorry, I don't think I can zoom that one in here. Right, so row 0, row 1, row 2, row 3, row 4. It's a little 5 by 5 maze. Right now we're going to see if we're not at the start, we have a step. Well, we are at the start, so there's no step. Because we're not counting that as a step. So now do we get to the end? No, we're not at the end. So now we're going to try, if it's not the start, put a breadcrumb down. Well, it is the start, no breadcrumb. So we'll try up. Can we go up? No, we can't go up. Can we go down? Yeah, we can go down. So we're going to call solve again. And if I step into this one, now we see there's another call to solve on the stack. So I've got the call to solve where row index is 1, column index is 0. I've got this call on the stack where row index was 0, column index was 0. So it has to remember all those variables, right? As we go, it's going to keep them all on the stack. So this one will say, okay, it's not the start, so we have a step. It's not the end. It's not the start, so put a breadcrumb down. Can we go up? We can't go up. Can we go down? Sure, we can go down, so let's go down again. So now I have a third call to solve on the stack, right? And now my maze looks like this. I've got a breadcrumb here. We're about to drop another breadcrumb here in a second. Now I got a breadcrumb here, right? So I'm at 2, 0. I just added my breadcrumb. It says, can I go up? No. Can I go down? Yes, I can go down. So let's step into that one. Now we have a fourth call to solve on the stack.
So one question. So whichever the first instance we find, like let's if we get down, like if you're able to move down, so right back it starts from the beginning, like start, right? So basically, if you have like 6 functions, like down, down, left, right. So whichever the first one it passes, it immediately goes back to the start, right? So it puts the breadcrumb and then it again starts from the
it doesn't go back to start because we're recursing with our whatever the current value was, +1 for row or -1 for column or whatever this happens to be.
Yeah, so my question is like, if say, let's say like it gets passed in number line 52, you won't go to 55, right?
Once this one's done,
it just get back to the first row. Oh no,
so it'll solve, so it's going to remember here in the call stack that we were at line 50.
okay.
After we finished all of as far as we need to go, it'll come back here and say, okay, well I did line 50, what's next? Now we look at line 52.
Okay.
So it's going to come back and try all the directions. We're almost there. Once we get down to the bottom, we'll see it. So got a couple more. So
what is meant by maze solver.start? What is that?
maze solve. So these are these start, end, wall, breadcrumb. These are the characters we're saying this is what makes up my maze. So it's just a list of characters. So maze solver is the class. Because they're defined at the class level, they're not self attributes. They're not, each instance doesn't have one. So you say maze solver dot this, and you get access to them. Yep.
If it was like an attribute, you would call like self.start, but it's a class attribute. So
Yes, you don't need the self. So like a lot of the functions in math, or like the values in math is math.pi. It's just a value of the math class. You don't need to have an instance of math to use the pi value. Yep.
There was some kind of method or something like that.
You can also make static methods. Yeah, we don't get into that yet. We'll do that later. Everything now is a instance method, instance function. They have the self attribute. Yep. So we've got another breadcrumb. Right now we went down to row 3. Right, we can't go up. We can go down. So let's recurse. So now we're at row 4. We got another step. We're not at the end. We add a breadcrumb. Right, so now we're at row 4. So now we'll see it starts to undo here because there is no further we can go. So I have 1, 2, 3, 4, 5 calls on the call stack. This one here can't go up, can't go down, can't go right, can't go left. So now it's going to undo the breadcrumb. Say, okay, well, it's not the start here, so let's undo the breadcrumb, take away the number of steps, and now we're going to see is we'll come off the call stack. So now we're done with this one. So we came back to line 50 here, where we were at row 3, column 0. And then we'll just continue on from here, trying the next thing. You'll say, can this one go right? No, you can't go right. Can I go left? No, it can't go left. All right, so undo the breadcrumb, take away a step. Now we're back at our call here, where our breadcrumb is here, row 2, column 0. Now it's going to say, okay, I tried down, I finished that whole path as far as I got, as deep as I got going down, 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 down. I'm back here. Now let's see, can I go right? Yes, this one can go right, so we're going to recurse going right. So it's not the start, I'm sorry, it's not the start, so we're going to add a step. It's not the end, so we'll add a breadcrumb. Now we're here. It's going to say, can I go up? Can I go? No, I can't go up. Can I go down? No, I can't go down. Can I go right? Yeah, we can go right to this space here. So we should go in and recurse in here. So we're adding to the call stack. Here we have a step. It's not the end, so add a breadcrumb. So now we're here. So the first thing we're going to do is try going up. Now we can look at it and say, we know that's the slow way. But because our code will always try up, down, left, right in that order, or up, down, right, left, it's always going to try it. So we know we're getting the bad path first. We can see that visually, that's okay, but it will try it. So we're going to follow this path going up first. So we have another step, so we're going to add our breadcrumb here. So we went up one, and again it will try going up. So we're going to go up again. We can go up, add the breadcrumb. Now we're all the way up here, so we can't go up any further, right? We're at row 0, so we can't go up, we can't go down because there's another breadcrumb, but we can go to the right. And we have a position to the right here we can go to. So we'll solve going one to the right. Add a step. And on, so eventually we'll get through, right, and we'll find the solution. So let me step a bunch here. I'm going to step out. I'm just watching the breadcrumbs here, so out. So now we're here, right? So we're at row 0, column 0. This is where we recurse. So we said, hey, if we're not the start, it's a step. Is it the end? Finally, we reached the end, right? 4, 4 is the end. Row 0, row 4, column 4 is the end. So now we're going to check for our best solution or not. There is no best solution, so the first solution we found must be the current best one. So now we have a best solution, and we still are going to undo. Right? We found one solution, we need to let all the other ones keep trying. So we're going to undo, take away the step. We tried down. Well, can we go right from here? No, we can't go right from here. Can we go left from here? No, we can't go left from here. So that one's done. So now we're going to undo the breadcrumb, take away the step. Right, so now we're back to here. Can I go up? Can I go down? Can I go left? Can I go right? Nope, can't do that. Undo the breadcrumb. So we're going to undo a bunch of breadcrumbs here. Unwind it till we get back to where we're at 2, 2, right? So these will all come off the call stack as we go. Undoing the breadcrumbs. So now we're going to try down, right? We tried up, we went as far as it could. Now we're going to just keep on going. The next thing we're going to try was down, all right? So now we go down. Now let's go add our breadcrumb. Can it go up? It can't go up. Can it go down? Sure, it can go down. So we're going to try going down. So now we're here. So let's add our breadcrumb. Right? It's going to try, can I go up? No, it can't go up. Can I go down? It can't go down. Can it go right? Sure, it can go to the right. So we'll go to the right. Okay? So we're going to recurse from here. Add a breadcrumb. So now we're at this location. Can we go up? No, we can't go up. Can we go down? We can't go down. Can I go right? Sure, we can go right. So let's recurse from that location. So now we're at 4, 4 again. Right? A different path got to 4, 4 with this recursive backtracking. So we found the end. We have a best solution. Now let's see, is this number of steps better than my current number of steps? Well, yeah, it is. This is shorter. Did not go around. So now we set that one here. We got a solution. And now we start unwinding. Right? We're done. Let's undo the step here and keep on going. Okay, I tried right. Can I go left? No, I can't go left. We're not the start, so take away the breadcrumb. Right? So eventually, all of these will just unwind here. We'll take away all the breadcrumbs, and the maze will be back to the way it started. Right? Took it away, take away the breadcrumb, take away the breadcrumb, take away the breadcrumb. And we get to the last call to solve, or the first call to solve on the stack, right? That tried down. We're at 0, 0. We tried down. We can't go right. We can't go left. We're done. Take away the step. We're done solving. So we've tried every single possibility here. And then, let's see, let's continue stepping, because I want to see this print here. So it should print. Right? So the shortest solution was 8 steps. So you can kind of see in here, right? We've got 1, 2, 3, 4, 5, 6, 7, 8. 8 steps to get to the end with this one. That make sense? So it's just trying everything with this backtracking recursion. Okay? There's another puzzle we can use backtracking recursion for, because I love puzzles, right? The same idea. We're just going to try something and see if it works, right? Oh, I didn't actually get into the whole function here. The can move, can go. I think we did that in the video, right? If it's a valid move, we did it. So this idea, each of them said, hey, can you do the move, then recurse there, right? Just adds a little check before we go and do it here. All right, so we start up add a new script here to this one. So we'll call this one N Queens. So there's a classic chess puzzle here. the 8 queens puzzle, and really you can do it for any value of n's here. Let's check out the Wikipedia page. Wiki. So the idea is, how can you put 8 queens on the board in such a way that no queen threatens any other queen? So if you're not familiar with chess, queens can attack anything in their row, anything in their column, anything in their diagonals. Right? So it's a lot of different things. But there's 92 ways you can solve this puzzle. 92 solutions. You can put 8 queens on the board without any of them threatening any of the other queens. It's kind of interesting. So we're going to see, can we find a solution to this puzzle here with our n queens puzzle? So we're going to write a class for n queens. Now, we don't need to inherit from anything. We already inherit from object, that's fine. So we're going to define our init method here. Now, I want to know what n is for this, because you can do it of size 8, you can do it of any sort of size, right? There's a whole, as large as you want to get for this thing, right? So 9 queens, 10 queens, on and on and on. So what does it say for, as long as it's 4 or more. 3 or less you can't, but 4 or more is fine, because that's what we know that you can do with this, right? Yeah, here's the n sizes here. Here's the fundamental solutions and all solutions, because this counts all the rotations here. So as you get to a 27 by 27 board, there's, oh goodness, billions, trillions, quadrillions, 29 quadrillion solutions. We're not going to do all of them. Even our computers are slow when it comes to that. But we can do, the n queens and get 92 solutions if we want. That goes pretty quick. I'm sorry?
Does your computer crash?
At 27 by 27, it won't crash because we won't hit the end of the recursion depth, or the deepest, because it will only have 27 calls, right? We say, hey, row 0, row 1, row 2, row 3, row 4. But there's so many different attempts it has to do to get all 29 quadrillion attempts, it'll just take forever. Yep. All right, so we know here's n number of queens. So we need a self.board equals a list of lists, and I'm just going to go copy paste this one in here from here because it's probably easier. We don't even need that. So we'll make the board as a list, and we'll say for row in range 8, or no, range n, right, because it's n size here. We'll say for column in range n, self.board.append a list. Sorry, append a list here for the row. So make an empty list. For every row, add a list to the list. Right? Add the actual row. And then for every column, take my self.board at the row index and append a space. So for n spaces in n lists here, right, that sets up for every row this many columns, right, for n here. Okay, and then I need a current row. This one's probably a private value here, so we'll say this is the current row is going to equal 0. We're going to start at row 0, or we can go column. Do you want to go by row or by column? What's easier? By row? Okay, no, go by row. So we're going to start at row 0. Okay, excuse me. And then I think that's all we need, right? And then we can have a method for solve here. And then we want a method for string. So let me get this string here. So for the string, I don't think we need anything other than this here. We don't need this number of steps here. We just need the solution here, and it's not self-maze, it's self-board. Right? So for every row on the board, turn it into a string, join them together with new lines. Okay? So we can represent this board here. So to solve then, just thinking about all the different steps we're looking at. So if we know that a queen can't go on a row that has another queen, we can simplify this a little bit. So if my current row is 0, I'm going to put a queen at row 0. If my current row is row 1, I'm going to put a queen at row 1. I don't need to look at row 0 anymore, right? Because there's already a queen on row 0. I can't get to row 1 until I put a queen at row 0, right? So those 8 or n rows here, as we go, are going to make sure I've filled out that number of queens, right? So I know there's a solution for these. So we're going to say for row index in range n here, right? Because we want to go for every row. And really, we don't even need to do this because we can say while my self.current row is less than my probably the length of n, maybe that's easiest, or length of self.board. So the length of my self board should be n. I could save n if I wanted, but it's also going to be the length of the board. I have that n number of rows, right? So as long as my current row is less than the length of my board, I can keep on going. Once I've gotten to where my current row is equal to the length, I'm done. Right? I found a solution. Excuse me. So now I know I'm going to put a queen at this row if I can. So now I can say for, we'll say column index in range length of self.board. Right? If we were to imagine doing this just by hand here, right? There's my chessboard. On an empty chessboard. Here we go. Here's a pretty chessboard. Can I make it bigger, please? Oh, goodness. Come on. Open new tab. There we go. So at row 0, right? This is row 0 here. We're going to see, can I put a queen here? Sure, I can put a queen here, right? Let me do this snippet here. This is fun. Now I can actually draw on it here. I should have brought my tablet. Come on. Where's my snip tool? Snip tool. Oh, do not disturb is on. That's fun. Come on. Snip tool. Why? I'm sorry?
I think we can paste it.
Yeah, I thought I did a snip. It's upset with me. My computer's unhappy. I'm sorry. Do not disturb is on. Snipping tool.
Just try and do.
Ah, this one. So we're going to put the queen here. So I'm just going to do an X instead of a Q. Is that okay? Because Q's are hard with the mouse. So we put a queen here. It can go here. So now current row will go up one. We're going to say, okay, now at row 1 here, can I put a queen in this column? No, because there's already a queen in that column. Can I put a queen in this column? No, because there's a diagonal here. Okay, so can I put it here? Sure, I can put one here. Go to the next row. All right, can I put one here? No, here, no, here, no, here, no, here. Sure, put one here. Go to the next row. Can I put one here? No, here. Sure, this one's open. Put a queen here. Go to the next row. Can I put one here? No, 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 because the diagonal. No, because the diagonal. Queen here. This diagonal's taken.
The fourth one.
Fourth, oh goodness, you're right, you're right. Okay, so undo that one. Fourth one. I got too excited. All right, so here, no, 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 no.
Can't do the first one. Oh, no, sorry.
Because this column, this column, this column, this column, this column, and then this diagonal. This. So if none of them work, I'm going to go back and undo. Right? Obviously, this one didn't give me a solution, so let's try the next one here. So we undo that step and just keep on going. Okay, let's try the next column. Not this column, not this column, not this column, this column. Then we're backtracking, right? Undo the last step and keep on going. All right? Can I go here? No, here, no, here, no, here, no, here, no, 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 no. That one didn't work, so undo. So undo that one, come back. This one must have been bad. Undo that one. Try the next column. Not that column, not that column, not that column, not that column. How about this column? Sure, let's try here. It's just going to literally try every single possibility here. So that's all we're doing. So for every column, let's see if we can put a queen there. Right, so we have the column index. We know what our current row is. So we can say if can place self dot can place at the row index self dot current row column index. Then we do it. So if we can, then we're going to go ahead and recurse. So we'll take my self dot current row +1 and call self dot solve. Now, solve doesn't need to be given all these other attributes. Like when we did the maze solver, we need to know what row and index we were at. For the queen's puzzle, we have this current row value that we're changing. We could do a similar thing with the maze solver and have a class level attribute for it. Both ways work, right? Passing less things is slightly more efficient, but this is fine. So we're going to recurse here. We found it. When this is done here, right? Whenever we come back here, we either found a solution or we didn't, right? So really we should probably be checking first. So if my current row is not less than the length of the board, right? We have this else case here, right? When it's no longer less than the length of the board, now I know I have a solution. So for now, let's just print self. So I know I found a solution. We'll print it out here.
So how does that mean that we found a solution?
So if the current row is not less than the length of the board.
So it's after the board.
So yeah, so like, because current row is going up one. Every time I can place a queen, I up a row, increase the row, increase the row. So after I hit row equals 8, there is no index 8, because if index is 0 to 7, I know I must have found a solution. So increase the row, hey, I placed queen at row 7 somewhere at one of these columns, right? Then we're good to go. So, oh, I'm sorry, before we recurse, I forgot, we need to actually put the queen down. So self.board at the self.current row, before we do that then, right? So self.current row at the column index is equal to a queen. Or again, we should probably have like, here's the open equals that, and queen equals a q, because this is just a little cleaner here. Put the queen down. Self.queen, or we can say nqueens.queen. Okay. So put the queen down. Increase the row. Recurse for solve. When solve is done, we need to undo those steps, right? So we will undo my increase here, and we will undo the mark on the board. So put it back to open. And then we just keep on going, right? If we found a solution, great, it'll print it. If we not, that's it. So what we need to do is figure out this can_place here. So we're going to define the can_place function. Now this one gets a little tricky, right? Because there's a couple things that happen. So we're looking at, is there already a queen in my column? Is there already a queen in my diagonal? Right? And now we know, because we're going in this particular order, I'm only ever going to look diagonally back. Right? No, actually, no, you have to look diagonally forward. Sorry, we don't ever need to look down. So we're only looking upwards, because I know there's only going to be queens above me. So I can look straight above me in my column, I can look diagonally above me, going back towards column 0, or I can look diagonally up, going towards column 7. Okay? So we're only checking those 3 directions. So we could break that up into 3 pieces if we wanted, right? Like we like to do. So we can return, I don't know, what is open column? Now, can_place, right, needs to know the row and column, right? Actually, I don't even think we need the row, right? We can probably just do for the column, because I know what the row value is. So we can say is open column, and this needs to have the column index. So if I give it the column index, let's see, hey, is that column open, given the column index? So it has to be open there, right? And it has to be open self.is open diagonal back, given the column index, right? And self.is open diagonal forward, given the column index. Right? Those are the 3 things you need to check. We need to check up, check diagonal back, diagonal forward. Okay? So we'll break that up into the 3 steps. So we'll have our is open, given the column index. Okay? So if the column open, so to do that, we're going to loop through every row going up. If we find a queen, we're not open. Right? So we can say for row index in range. Now I only need to go up to the current row. Right? And you'll need to look at rows from 0, 1, like whatever to that current row is. Right? So if my self.board at the row index at the column index is equal to a nqueens.queen, you can return false. It is not open, right? Because I found a queen, either at 0, 1, whatever previous row indexes. So keep the column the same. Column's always the same. Look at every row starting at index 0 up to my current row. Because I don't need to check my row, right? Because I know there can't be a queen in my row because we're trying 1 row at a time. If we've gone through every row and haven't found a queen, we can return true. It's open. The column's open, right? So this just checks the top row at my column, the next row at my column, the next row at my column, the next row at my column to see if it's open. Okay, then we can define my is open diagonal back given a column index. Now this one, so going back towards column 0, right? So I want to go for, this will be my row index. I want both values, shoot. So maybe we say, while, oh goodness. Because we're going to go minus a row, minus a column. Minus a row, minus a column. Minus a row, I should be going this direction for you guys, right? Back towards the top corner, right? So how about we say current row index is equal to self dot current row, and my current column index is equal to the column index, and while my current row index is greater than 0 and my current row index is greater than 0. Greater than or equal to. 0 is still valid, right? Right? As long as we're 0 or more, we're valid. We have more rows or columns to check. If either one of these becomes non-zero, less than 0, the loop should stop because that's an invalid index. Well, technically it's valid in Python, right? Because you can do negative indexing to get the other side of the list. That'll do really weird things to us. We want to stop, right? So let's go, let's check. So if, and now I don't actually need my current column, right? I probably want to start at -1, -1 already, because I don't need to check where I currently am. So let's start at -1 and -1, right? Let's go up a row, back a column to start, because that's the first one I want to check. Right, this direction for you, sorry. So if my self.board at the current row index at the current column index is equal to an nqueens.queen, return false. Otherwise, take the current column index -1, take the current row index -1. Just keep on going, right? As many rows or columns as we have, keep on going, backing up until we either fall off the column or fall off the rows. Right? If we found a queen, false, it's not open. If we've gone through this entire while loop, we haven't returned false, we can return true. That diagonal back is open. Right? Okay, now the same thing works for us here. I think I need my backslashes here, is that why? For diagonal forward, it's just slightly different, right? Because we're going to go up a column instead of down a column. Okay, so this will be for forward. So my column index then will be +1. We're going to say, well, my column index is less than the length of self.board, and the row index is greater than 0, because we're going up a row, up a column. This direction now, right? Up a row, up a column, because you're going diagonal forward, right? And if it's no good, right, or if you didn't find a queen, keep adding to your columns to keep going forward columns to look your diagonal forwards. If we ever return to false, return true. That is it. That's the nqueen solver. Why is it unhappy? Oh, they should be tabbed, right? Is that why it's unhappy? There it goes. I don't like these lines. Too many blank lines. Okay. They're just warnings, but that's fine. So we should be able to print every single solution here, because we're just going to print if we found a solution. That's the only thing it does, right? And then it undoes, right? Undoes the row, undoes the queen placing. Okay? Oh, I misspelled forward. There we go. Forward. That's nice. Where did I use that? This one, forward. I love how it spell checks in my IDE. That's super handy here. Okay, so back in main here then, we should be able to do, it's the maze solver, sure. We should be able to take in n queens, or I'm sorry, so let's do, I don't know, 8 queens equals an n queens of 8. And then call 8 queens dot solve. Oh, we got to import, sorry. So from n queens, import n queens. Okay. So let's do size 8, let's solve it. We should get 92 solutions. It's a lot of solutions, but that's okay, right? Give it a try. Uh-oh. It's stuck somewhere. We didn't find any solutions. So something's not happening right. Okay, here we go. Let's see. Solve. Find 53 Ken place for a column index. And queens. Got stuck somewhere. So let's see it. Let's put it in debug mode and see what happens. Let's go back to solve and run main with debug mode. So we don't want that one. That was our maze solver. So now continue. Don't want that one. That was our maze solver. Continue. Right? Oh, nope, that was the one I wanted. Sorry. Hey, we paused. Okay. So our current row, right? Self dot current row. Do we not have, where's current row? Oh, it's current row is 5. So our board then should be, got a bunch of queens here, so now we're going to be in 5. Okay, so current row is less than the length of the board. Let's see, where's it going here? So that's step. We're going to check column. So column here. If we can place it that column, no. Can we place column 1, column 2, column 3, 4, 5, 6, 7. We'll go back to my current row. Oh, we never changed current row. So if this doesn't work, when this is done, right, we need to go back and undo that step. That's what was happening. So we got stuck in this loop here. Shoot. So if we've tried every single possible position and it didn't work, we need to undo that one here. So at the end of this for loop then, right, we want to undo the queen and go up a row. So I guess maybe this should happen. Have it in here twice now. Solve. I'm trying to remember. So it needs to be back one, right? So if we can place current row, I think it should be at the end of this loop here. So at the end of that loop, do we go back one? Should we keep on going and going and going and going? Let's try it here. Let's try a loop else here. Oh, it doesn't have the current index though. Shoot. All right. My undo step's in the wrong spot. Sorry, I'm trying to remember off the top of my head where it goes. So for column index and range, if we can place, great. So if we can't place, right? So okay, so if we can't place at the end of that here, then we want to undo the queen we just put down. So we can place. No, okay, so this was fine here. This was the undo step. We just need to end this loop here because it's just being infinite now with this while loop. So when this loop is done, right, when this for loop is done, then we want to, we're gonna break? I think we break. Or return? Maybe we just return. We just want to stop this function here because once we've reached the end of all of our columns, we're done. We want to go back to take away the row, undo here. This is after all 8 columns or all n columns were tried. Go back and undo. Right? So that ends after this one here. To make sure that it ends. Okay. I think this will be happier here. Okay, that else is. I think that's fine. Let's try that. Okay. Let's give it a run. Oh, need to run main here. Run main. Hey, okay, now we get some solutions. And there's probably, we could probably count them too if we wanted. Would that be fun to count them? So can we have like a solution count? So self dot number of solutions is 0. And if we find one, right, so at the end of our solution here, right, when we print ourselves, we'll take 1 plus 1. And then when all of that's done here, or maybe even print that. So we say self and then, there we go, print. Print solution number, self.number of solutions. You think that'll work? Let's give it a try. Yeah, solution number 92. Solution number 91. Awesome. So let me do one more print here. Break it up a little bit more. So you see all the different solutions. So eventually, right, this is just a rotation of another one, a mirror of another one. This having this go back step was important. This is where it was broken before, right? Because it just never, this loop never ended without it here. So this stops that loop from running. After you've tried every column, just stop. It might be better to do this as a for loop, because that would have stopped it too, right? Because I think the while loop was probably bad. So maybe a for loop would have been better there than a while loop, because I wouldn't need the return. Yeah?
In real life, what is recursion used for?
So you know how like you can have a folder, and the folder could have folders, and that folder could have folders, and that folder could have folders? Without recursion, how would you say, hey, how many files are on this computer? So recursion says, okay, well, count all the files. If there's a folder, recurse. Count all the files. If there's a folder, recurse. So some structures naturally work well with recursion. And when we get into later, we start talking about trees and things, the recursive nature of this stuff just makes it really easy to deal with. Not everything you can use recursion for, and that's one of the important pieces, right? Everything that can be solved with recursion can be solved without recursion. But not everything that can be solved with recursion. It only works for certain cases. Right? You have that idea that you have to have a base case. The base case is, I know what the solution is. It's done.
When it should stop, right?
Yeah, when we stop, right? I found a solution, or I found a game over. I found an end. It stops. And then the other thing you need is, how do you take something that's not solved and get it closer to being to that base case? So take the complex problem, can you get it one step closer to a base case? If you can do those two things, you might be able to solve it with recursion. So for like the file system thing, right? If you find a folder, you're not done. You can recurse. That you can approach the base case by saying, okay, go into that folder and look for more folders and count the files. Eventually, you stop finding folders and you reach that base case. There are no more folders. Now I can just add up all the files I found. Right? For our backtracking, right, I either reached the end and I can't solve it, or I found a solution. If not, we just keep on trying these things. And then again, some of the data structures we work with are really fun. You can use recursion for that little the idea of the binary search. We did like the number guessing game. You always split the difference in the middle. You can use recursion for that. You can say, okay, let me just take the next step with half the list, and take the next step with half the list, take the next step with half the list, take the next step with half the list, over and over and over. We can do it without, right? We did it with a loop. We just say, while we're not at the number we guessed, right? We can use a while loop. So some recursion can be replaced with a loop, some is harder. There's this Tower of Hanoi puzzle, which is really fun. Done in Python, which is fantastic. I want the animation here, Tower of Hanoi animation. So the Tower of Hanoi is this, I don't know who came up with it here. You have to move these disks from one peg to the other peg. Good solution. So if there's 5 disks here, and I want to get them from this peg to this peg, but the idea is here you can't put a bigger disk on top of a smaller disk because you'll crush it. And the legend is there's monks somewhere moving 21 disks, and when they're all moved to the other peg, the world will end or something like that. Whatever. It's just a story. So to do that, it's hard to move 5 disks, so we can't move 5. But it's easier to move 4. Well, 4 is hard to do, but I can move 3. Well, 3 is hard to do, but I can move 2. Well, 2 is hard to do, but I can move 1 disk. So to move 1 disk from here to here, easy. The next step then is moving 2 disks. Well, moving 2 was, I already did the top one, so let's move the second disk to here and put the first disk back on top of it. Now I've moved 2. Okay, well now I need to move the third disk. I'll put the third disk here and then move 2. Well, 2 is hard, I can move 1. So move 1 disk here, move the second disk here, move the first disk back on top. So it forms this really easy, natural, recursive pattern where it's hard to do anything more than 1. But once you get to 1, it's really easy. So it shows the solution is really fun, right? We move 1, and we move the second one, we move 1 back on top. And we move the third one, and we repeat the process of moving 2. Moving the fourth one then is, I moved 3, now I can move the fourth one, and then repeat move 3, which is repeat move 2, which is move 1. It breaks it down step by step by step. So now I've moved 2, now I can move the third one, and I repeat the move 2 again. So just the nature of this problem can be solved very easily with recursion here. And that Python solution is really 6 lines of code. That's it. That's the recursive solution. Doing this without recursion takes lots more code because you have to track all of these things here. So we're just saying, okay, if n is 1, move 1 disk. If it's not 1, move n minus 1, and you flip where they're going, right? So instead of the destination, you're using that spare peg for the n minus 1. Then you move it, and then you move n minus 1 again, flipped again.
So like you use recursion when you call a function inside the function itself.
Yep, when a function calls itself, that's recursion. Yep. Right, so here's that basic solution, right? How do I get these 3 onto peg C? Right, we'll move C, move the first peg, move the second peg, move the first peg again, move the third peg, move the second peg, move the first peg, right? So it's, for 5, 4, 3, 2, 1, and then it's 2, 1, and then it's 3, 2, 1, right? And then 4, 3, 2, 1. Like, you just keep on going over and over and over again here, which is fun. So that's the Tower of Hanoi in Python here. I think the animation is almost done now, right? It's a slow little thing here to move them all. So now I did 4, now I can do 5 and then do 4 again. And 4 is 3 again and 2 again, right? So it's never a very deep recursion, right? It's the number of disks that we have is that many function calls that will be that deep. So I could do 40 pegs here if you wanted, right? So we could do 40 pegs. Let's do a speed factor of times 50. 3D is more fun here. No, I wanted 40. No, didn't it say 40? I don't know. Oh, that's right. Disks, it was 40. I don't know why it's not working. But with 9 disks, right, it's 511 moves. You shouldn't. It should only, because you just repeat the process. So like,
yeah, you only need 3.
It just keeps on going.
Non steps, I think, based on each disk. Like, adds
Yeah, it's like a factorial or something, or there's some math there for.
it's 2 times more steps. Yeah, because 2 to the 9 is like 512. Yeah, it's 2 times more steps.
Yeah, okay, so to the end.
Nice.
Yep, and this is with only 9 disks, right? I don't know why you have more pegs. I never understood why they had that there, but because every time you do a step, you have to do all the previous steps again. So when we looked at the Fibonacci sequence, did we do that in the video? Did we talk about Fibonacci? The better fib? Honestly, I don't remember. My bad. All right, let's look at Fibonacci here real quick.
0, 1, 1.
Yes, 0, 1, 1, 2, 3, 5, 8, 13, 21. It's the previous 2 numbers make up the next number here. So Fibonacci, fine, fib, because I can't spell Fibonacci. If you tell me what nth you want here, right, I can solve it. So it's if nth is equal to, or we'll just say less than or equal to 2.
That's your base case, right?
Your turn, yeah, so our base case is, if you want the first or second Fibonacci number, it's a 1. I just know what it is, right? Because I can know that solution. It's done. Otherwise,
But what is meant by return 1? What
so
do you return 1?
the value 1. Because if you want the nth Fibonacci number of 1 or 2, it's 1. Otherwise, I have to go calculate something. I just know the solution here. Yep. Otherwise, now we're going to have a fib here of nth. We'll have the previous and the current nth. Right. So if it's not that here, right? No, I'm sorry. So if it's not less than that, we're going to return fib of nth minus 1 plus fib of nth minus 2. Right? That's the mathematical definition, right? It's the sum of the previous one and the previous number in the sequence. This will solve Fibonacci for me. So if I want to, I can say for, I don't know, n in range, let's go like 50 here. Let's print fib nth of n colon and fib of, call the fib function given it n, right? So the first, let's start at 1 here because 0 doesn't really make any sense, right? So starting at 1, going up to 51 here. Let's print some Fibonacci numbers. First ones are really quick, right? And now start slowing down here. Because what my computer is doing is it's literally adding up the number 1 that many times. Because when you call Fibonacci of 9, it says, okay, well, what's Fibonacci of 8 plus Fibonacci of 7? Fibonacci of 8 says, okay, well, what's Fibonacci of 7 plus Fibonacci of 6? Fibonacci of 7 says, okay, what's Fibonacci of 5, 6 plus 5? 6 says, what's 5 plus 4? So you get this like exponential branching. I think this one's factorial out. number of function calls here. And again, there's not a lot of them in the stack because it will do 41 is 40 plus 39 plus 38 plus 30. So we'll get n number of calls in the stack. It's not going to crash. It's just terribly slow.
Is it still calculated?
Yeah, it's adding up the number 1 millions of times now. So it's 267 million function calls to Fibonacci have been called. Because I have to, the only time I ever get a value is when it's 1. Other than that, it's the previous one, the previous one, the previous one, the previous one. So we could see it in the call stack if we wanted at some point that it's this many calls. It's just terribly slow, right? So obviously this is a bad solution. Right? This is Fibonacci, let me call that slow. Right? So this is ridiculous number of them here. So a faster way to do it then is have that fib function of nth. Again, we know what the base case is. So if it's less than 2, we do this. Otherwise, now I can use a helper function here. That is the nth, the current nth, the previous, and the current. You can say, okay, so if you tell me all these things, if my current nth is equal to the nth, I'm going to return previous plus current. Otherwise, I'm going to return this helper fib function of nth is the same, the current nth plus 1, my previous is now the current is now the previous plus the current, right? So go to the next one in the sequence, So if Fibonacci, if I want the third one here, so we'll return fib of nth here, the current nth will be 2, right around 2, and then 1 and 1. So if I wanted the third number here, it's not that, so I'll recurse. So nth was 2, goes up to 3, current was 1, right? So my previous is now 1, my next one is now 2. Now I found the next number, and I can return. I think that's the one, or maybe I just give it current. So this will be faster because I don't have to add up a bunch of 1s. I'm adding up to the number here, right? Because I'm adding my previous and my current values as I go.
Okay.
Is the next value, right? So I think,
the one keeps going back to it here.
yeah, yep. So if we give this one a run here, now it didn't even like pause, right? We just got all the numbers out here really quick. Because now we're adding up 50 times rather than adding 29 million times or billion times, adding the number 1 together. So this is better. But the idea with this is it's really just a loop, right? I don't need any of this here. I don't need recursion for this because all it's doing is looping here. So I can define fib iterative, given an nth here. And again, same base case here. Other than that, I can say my current nth is 2, and while my current nth is less than the nth here, right, let's keep on going. So I'm going to have current nth, I'm going to have previous is 1, current is 1, and while we're less than, I'm going to take my previous, I'll say next is equal to previous plus the current. I'll say my previous is equal to the current, and my current equals the next. And I'll take current nth plus 1. Right, find out what the next value is, move current back 1, move current to the next value, and keep on adding. So it's a loop here. So all we're doing with this recursion is looping. So we can just write it with a loop. Right, we don't need any of that other stuff here. So it should be the same fib nth, and then let's also print using fib iterative of n. So we should get the same numbers out if we did it right. Uh-oh. Oh, I forgot to return, sorry. So this one should, when this is all done, return current. Right, when the loop is done, when I reach the value, make sure I return current. That way I don't get my nuns. Let's try it again. Right, so I get the same values out. So with recursion, without recursion. For Fibonacci, doesn't make a difference, right? The Tower of Hanoi solution, right? So Python Tower of Hanoi without recursion. Right? Non-recursive function. Basically this. So he had some problems here, but basically this. This sucks, right? Compared to this one, right? So technically this will be faster because recursion does have a cost to it that it takes some time, and every time we call that function, Python has to track all of the variables. So when we call Fibonacci here, this helper function here, this is my helper private function, we're essentially storing another copy of nth, current, nth, previous, and current, because any arguments have to be stored in that call stack for that function. So we're storing, if I want the 50th one, I now have 50 times 4 values in memory. For our purposes, we don't really care. It's not that big of a deal. It's not that much more memory usage here. But fib iterative does use less memory because I don't have that number. I only have the current nth, the previous, the current, and the nth here. I only have 4 values ever that I'm storing, not 4 for every time I call this function. So a little bit more efficient. But these can be harder, right? So the non-recursive solutions can be harder for things that recursion is good at, right? So like the Tower of Hanoi is a really classic example here, this sort of thing. Okay? So we'll practice for lab. We'll do another puzzle, and it's another chess-related puzzle because chess is fun. It is the Knight's Tour puzzle, just if you're curious, Knight's Tour. So this Knight's Tour puzzle says, given a chessboard, how can you take a knight and move to all 64 squares without repeating a square? It's a Hamiltonian path problem in graph theory. That's super exciting to know. It's actually really interesting, but this is solvable here. So the interesting piece is like, how many valid moves do you have from any given location? Well, in the corners you only have 2, then 3, then 4. So the edges are the least number of moves. As you get towards the center, you have 8 possible moves in all directions. You want to make sure we don't re-step on the same square again, right? So how do we find those solutions? So it's neat. And then the number of possibilities is actually crazy here. And if we don't add this Warnsdorf, I'll get it. I'm bad at English. I can't even try other languages here. You want to make sure that we use this heuristic here that says we want to have the fewest possible onward moves. Now we can solve it quickly. If we don't implement this, we get stuck in the middle where there's 8 different possible moves and 8 different possible moves, and you quickly hit 19 quadrillion, centillion, right? That's billion, trillion, quadrillion, 19 quadrillion, and you just get stuck forever. So we can reduce that very quickly with Warnsdorf's rule. We'll do it in lab. That'll be the lab exercise. Do a Knight's Tour. Okay? All right, it's been fun. Again, so I won't be here Tuesday, apologize. I'll have the recorded video, and then we'll have the lab exercise. If you want to try it, great. I can answer questions about it next Thursday if you want. The project is due next Thursday as well. Before class, I'll go over my solution in class. Okay, that's the plan here. And then I think that's about it. Let's see. We had the next chapter is really boring here, right? Array-based sequences. Because Python has the list object or the list thing built in, this is really dull. Other languages don't necessarily have the very flexible list like Python does, and you have to do a lot of work to make your arrays flexible, like lists are. So it'll seem a little silly, but we'll look at it as well, okay? All right. No. So you can use arrays in NumPy. They've got the static arrays because they're slightly more efficient as well. All right, I'll see you next week then.